Hey students, I got a question here on problem number 39 here from our homework. Actually, I guess it's the advanced book, the university physics, so it's actually chapter 12 in terms of that book, but it's in our main book, the topic of chapter 9. So you'll find it in the syllabus under chapter 9, but then problem number 39. Printing up the problem, here is the diagram, and let's kind of go through this, and I'll begin by just kind of reminding you of the important fundamentals. That is, if you have something that is, static, stationary, and in this case, it's somebody's forearm, they're using their bicep muscle, they're holding this heavy weight, and what they're trying to say here is it's stationary. So knowing from past chapters that the sum of all the forces equals mass times acceleration, if something is static like this, the acceleration would be 0. And so we like to say, take all the forces, add them up, and you'll get 0. And it needs to be said that that would be true left and right and up and down. So the forces in the x direction have to add to 0, and the forces in the y direction have to equal 0. And then more recently, we got into more advanced mechanics where things rotate. And rotate, we had then what we called the second law of rotation, where instead of looking at forces, we were looking at torques, and instead of looking at mass, we were looking at a moment of inertia or a second moment. And then, of course, instead of translational acceleration, we had angular acceleration. But same logic here, that if something's going to be stationary or static, not only does it not move left and right, it also doesn't move up or down, but it also doesn't rotate. And so that means the angular acceleration would be 0, and that means the sum of all the torques would be 0. Now, if you restrict your forces to be, in the xy plane, like on this sheet of paper, then the only thing these forces can do is rotate on around a z-axis, an axis pointing towards you on the screen. So we would like to say then that we have only torques around a z-axis, so the sum of the torques would be 0. And so these would be our 3 equations that we have to satisfy in order to have an object at static equilibrium. And so this is my joke, but somewhat serious. If you'd like to know the answer to all the homework problems that are static, this is it. This is the first equation, this is the second equation, and this is the third equation. And then you just have to fill in the details and finish the problem. So that's kind of the thinking behind our strategy. Now, just as a side note, obviously the world could get much more complicated in 3 dimensions. You could have forces in the z direction. And so we would say we don't want it to move left or right. We don't want it to move up or down. But we also don't want it to move forward or back. And that would then have another term here, the sum of the forces in the z direction. Now, of course, that being said, then if you have a force in the z direction, like if I lift up on the top edge, I can then get a rotation like this. And that would be a rotation along an axis that is the x-axis. So then we would have torques around an x-axis and torques around a y-axis. So I guess I'm just throwing that out there for in general, but a good educational place to start is the simpler case, things in a plane. Those are hard enough. So let's look at just forces x and y. And so they have to balance so that it doesn't move left or right or up or down. And then let's realize that those forces could create a rotation, but only around a z-axis. And so this is the foundation. All right, well, hope I didn't take too much time with that. Now we can actually then do this problem. It says the forearm below is angled at some angle, when they say theta, with respect to the upper arm, and that we have a 5 kilogram mass and it's held in the hand. The total mass of the forearm and the hand is about 3 kilograms with its center of mass 15 centimeters from the elbow. What is the magnitude of the force from the bicep muscle? All right, well, I'm going to draw a new free body diagram that's a little simpler. I'll just put a little dot for the joint here. And so here is that point where the forearm can rotate around whatever bone that is, but the bone in the upper arm. Okay, and so as it rotates, right now I have it at this position. And so this angled line is the forearm bone, and this is the bone from the near the bicep. But right here then, there is a pulling up, I'll call it F, of this bicep muscle. So this bicep muscle is contracting and lifting up the forearm. Because what's pulling the forearm down is this large 5 kilogram weight. And so there's our mg pulling down on whatever we're holding here. But also what's pulling it down is just the weight of the arm itself. And so it says the total mass of the forearm and the hand are 3 kilograms. And you can think of that as their center of mass at 15 away. So maybe right about here then is 3 times 9.8. And I'm not sure I kind of gave myself enough room to show this well. But back here in this diagram, this distance is a 4. And they didn't even show it here. I think part of the reason is they wanted you to add it and not give it away, is this is 15 centimeters. So from here to here is 15. And that's the force that's not included in the diagram. I guess actually none of the forces are included in the diagram, I guess, because they don't really give a force of the bicep, but at least they show it. And they don't really give a force here, but they do show it. Anyways, and then this is also given in the diagram. This whole distance out is 35 centimeters. Okay? So what I'm going to do then is say for the torques to come out to be 0, so the sum of the torques in the z direction have to be 0, I'll give myself 3 little placeholders here because I'm going to have then 3 torques. One torque is coming from the force of the bicep muscle, that's pushing on it. Another is coming from the gravitational force, that is the weight of the forearm and hand. And the other one is the weight of whatever is being held there, that sphere. Now, by the way, there also would be forces at this joint. But maybe it's worth reminding ourselves, this is what we need to do right now, is torque is perpendicular distance times the force. And so it's not just how much is the force, but how far perpendicular is it at. And what we mean by perpendicular is if we draw kind of this line of action, we can then go straight out. So we're drawing a line perpendicular. So we don't draw it directly to where the force is per se, but we don't draw a line of action and we go, okay, how far out? So you can see that that's going to be less than 35, and so let's have a discussion about that. But that'd be our perpendicular distance. And what I wanted to say here is then in the joint here, where the bones come together, we might have a bunch of forces, but we don't have any distance. So the torque, I'll call it J for the joint, is going to give me a 0. So that's why back here in this equation, I put 3 placeholders for the 3 forces that are a distance out. And right here, I didn't even draw the forces. Maybe I should. Maybe I should even just make them stand out. I don't want to make them look too different because they are just forces, or a force. But I also just want to emphasize that I don't need to use it in order to do at least this step. Now, I think I'm going to need it later on. Let's come back here to the question because it says, A, what is the magnitude of the force that the bicep muscle exerts when the forearm is at 60 degrees? And then B, what is the magnitude of the force on the elbow joint right there? See, so I am going to have to eventually address these forces. So why don't I do this? And I say forces, and it said forces, or I guess it says force, magnitude of the force. It's kind of nice, since we don't really know what direction it would be, to draw kind of an up arrow and say there would be a certain amount of force in the vertical direction and maybe a certain amount in the x direction, and of course put those two together with Pythagorean's theorem to get the total magnitude of the force. And so that's what we'll do in the joint, but that's for really part B. So let me keep moving along here in part A. So I'll say it again. I'm going to set the torques equal to 0. I'm going to have 3 placeholders for the 3 torques coming from the force of the bicep muscle, the weight of the forearm, and the weight that's in the person's hand, but don't need to worry about the forces in the joint when it comes to calculating the torque. All right, so I'll just go in order. Let's do the bicep muscle. The bicep muscle, then, is what I'm looking for. So using this equation for torque, I'll just put an F here because that's unknown, okay? Now, the perpendicular distance, kind of in this diagram, and maybe I should do this diagram because it's a little bigger, and so I'll look at this, but I think you can kind of see it would be the cosine of that angle. Maybe I'll kind of redraw. Here's the joint. Here is the forearm. Here about is the weight of the forearm. Oh, I'm sorry. I'm going to do the bicep first. Sorry. Bicep. Here's the bicep. This distance is 4. And I think you can see that whatever this angle is, I'll call it theta for a second, that cosine of theta would be this adjacent piece. That's the perpendicular over the hypotenuse 4. Or put another way, the perpendicular distance would be 4 times the cosine of that angle. Excuse me. So that's what I need to put here is 4, and maybe I should be careful. That would be centimeters. So I better put 0.04. Okay. So in meters, it's 0.04. And then, I don't know if I gave myself enough room, but that would be cosine theta, and then the force from the bicep. Now, the other thing I need to do is to decide if this torque is a positive or a negative. And remember, things that rotate counterclockwise are positive, at least tradition. You don't have to stick by that. But the other direction's got to have a different sign. And so I'll do this to tradition, where counterclockwise is positive and clockwise is negative. And so this bicep muscle would be pulling the arm this direction, which is a counterclockwise, and so it should be a positive there. And in fact, with that mentioning, you can kind of see then that the weight of the forearm and the weight of whatever this person's holding is going to make it go clockwise. So I'll just put a negative and a negative for the torques from the other two. And then, of course, the other two, and I'll do the torque right here from the weight of the forearm as this next one. The weight of the forearm is 3 times 9.8. And the distance kind of follows that same logic, 15 out. So this distance is 15. But you can see, like we just did for the bicep, it would be 15 times cosine of that theta to get that perpendicular distance. And let me convert the 15 into 0.15 and then cosine theta. And then the torque from that heavy sphere out there would be 5 times 9.8. The distance out, and that's why this one is going to be the most torque. Not only is it the heaviest, but it's the further out, or furthest out. That'd be 0.35, and that would be cosine theta. Okay? So, let's see what I've got so far. Maybe I'll do this. I noticed that all of them have a cosine theta in it. So if it'll be okay, I might factor out the cosine theta. Yeah, maybe that wasn't such a good idea. Because I do want to multiply all these together, and I do know the angle. Yeah, that wasn't such a great idea. So let's talk about the angle. I was going to weigh in on the angle. But coming back and maybe drawing this picture again, all right, so here is the forearm. Okay, here's the bone of the upper arm. The angle I've been calling theta is this. And I want to maybe emphasize, and I should have called it something different. Because they gave us this angle, which they called it theta also. Well, without going back and changing the name of my theta, let's just say there's two thetas on here, okay? And their theta is the 60 degrees. But my theta is what we would call the complement of that. It's down here between the horizontal and the forearm, whereas their angle is between the vertical and the forearm. So in other words, mine must be 30 degrees. This picture here, if this is 60 degrees, this makes a right angle, so this must be 30 degrees. So I do know this angle. And that's why I said probably best if I don't factor it out. This is actually 30 degrees, 30 degrees, 30 degrees. All right, so let me put the equation here. So this is saying 0 equals, and grabbing my calculator and checking if I'm in degrees. Okay, good. I could do this first calculation, which is 0.04, and multiply it by cosine of 30. So this is going to be 0.0346 force from the bicep muscle. And the second one, and for that matter the third one, I know all these numbers. And so let me put those in. I'll think of them as both negative and group them together here. So this would be a 0.15 times cosine of 30 times 3 times 9.8. Excuse me again. Let me put this one together, which is the 0.35 times cosine of 30 times 5 times 9.8. And so this would be 18.67. And I think that's, yeah, so we know everything. We combine them together. And so now you can see we have a very simple equation that we can solve for f, because we can then move the 18.67 to the other side. That would leave just this, and then we can divide by the 0.0346 and get the force from the bicep muscle. So let me just divide by, and in this case I'll just go up and copy and paste that number. And it looks like 539 is the force from the bicep muscle. Yay, and so there's A. No, yeah, A, bicep muscle. What is the magnitude of the force that the bicep muscle exerts on the forearm? Now, for B, we need to include this forces at the joint. And as I was saying at the beginning of this video, that I can do the torques, sure, but it also must be true for these two options. So let me do the boring and easy one right here. Let me add up the forces in the x direction. And of course, say that those have to add up to be 0. And so as I look at this and come back to my free body diagram, which is getting kind of messy here, but starting over here on the far right, this force, which is the weight of the sphere, doesn't have anything in the x direction. So that would be a 0 in the x direction. And the weight from the forearm has 0 in the x direction. And the force from the bicep muscle is straight up, so nothing in the x direction. And then finally getting to the unknowns, the force from the joint, where I said, well, I don't really know what direction, so I don't want to draw something, and I'll just draw the components. I'll say it's made up of a x component and a y component. So the x component would be force in the x, and then you can see that we come to the conclusion that there would be no force in the x direction, at least in this case, the way the arm is oriented. And so it kind of makes sense because these other forces aren't doing anything in the x direction. And so if there was any x here, then we would have an acceleration, and that is the, arm would move in the x direction. And that was kind of the gist of the problem, that there is no acceleration in the x direction. So that's why I said this was not only the easy, but kind of the boring and obvious one that, okay, so no force to worry about there in the x direction. The more interesting one, and still not hard mathematically, but nonetheless interesting compared to the x, but I say not hard mathematically because it's not as hard as the torques. You can see that the torque calculations are pretty hard. You can see why we started with forces and not torques when we, started teaching the class. It's kind of useful to have students really kind of get a good handle on adding forces together first before we get to the more complicated rotation stuff. All right, so continuing on here and saying the forces in the y direction have to come out to be 0. Let's come to this free body diagram. And I'll just start on the right here and work to the left. But so the force from the weight of the sphere is this 5 times 9.8, and that's downward. So all the force from the weight of the sphere is in the y direction, and it is negative. And likewise, the weight of the arm, right here, it's all in the y direction, and it's all negative, okay? Now, the bicep muscle, which we just solved, that's 539, is upward, 539, okay? So that is lifting up. And then this one, which I've labeled as up, I don't really know whether it's positive or negative, but that's good. That's what I'm going to solve for. I'm going to find out right now. So I want to emphasize that even though I've drawn this upward arrowhead, I'm not really saying it's upward. In fact, giving me some rough numbers, the weight down, that's about, let's see, that's only like about an 80. So this is way bigger up than these are down. So this actually tells me I need some more down. So this is going to come out to be a negative one. But again, that's the kind of neat thing in the math that I'm not really saying it's up. What I'm doing is I'm solving for it. I'm solving to see if it is a plus or a minus. All right, so now I can put in my numbers here. And maybe I'll just put these three together. So this is a negative 5 times 9.8. Let me subtract a 3 times 9.8 here. Let me add a 539. And this comes out to be 400, and I'll round it to a 61, plus force in the y direction. And don't forget there's a 0 there. Okay, so finally, I can then shift this to the other side and see that I have a negative number. And putting in my units for both of these, since I did everything in meters and in kilograms and in meters per second, that should have come out to be newtons, and so should these, and so that force should be in newtons. So all my forces should be in newtons. Anyways, but there it is. There's the answer to B. How much force am I getting? And it also kind of makes sense if you kind of think of this a little bit differently. You could think of this rotational problem as pivoting kind of where the bicep muscle is touching, so kind of right here. And so these two weights are making the whole forearm rotate clockwise around the bicep connection. And so we would need the force from the bone to push back, that is down, in order to hold the forearm muscle from twisting due to the weight. That bone has to leverage in and kind of jam it and stop it from rotating. And so that's why, again, another reason why I would say it's got to come out to be a negative number. And I would even say a significant negative number, because the distance from this kind of pivot where the bicep is connected is just short compared to these other ones. And so I've got two of them over here. I got only one on this side. So this one has to equal these two torques, and they're further away. So it's got to be a big force. And sure enough, it is a big and negative force. So good. Conceptually, it all seems to make sense, and mathematically, it comes out perfectly. Okay? And so that's awesome. Now, in all of this, I think we've kind of indirectly answered C, where it says, how do these forces depend upon this angle? Okay. Now, of course, they're talking about their angle, not my angle. But you can see as their angle, say, gets bigger, so if the 60 goes up to a 70, my angle, my theta, is going to go down to a 20. And I wrote my equation here in terms of cosine of the angle. And so if you could imagine my angle getting smaller, going from 30 down to 20, and the function, if you will, would get bigger, maybe it's worth drawing a picture of the cosine function. You might remember that starts at a 1 and then crosses at 90 degrees and becomes negative. Becomes -1 at 180 degrees. But in my case, We did this problem with my angle at about a 30 here. But if their angle gets bigger and mine gets smaller, so mine gets here at a 20, then this cosine function is getting bigger, and therefore my f here is going to come out bigger, since looking, let's see, where am I? Yeah, so it would show up and make this significantly bigger. I guess technically make that a little bigger that I'm dividing here by. But that's probably best to look at it in terms of this factoring piece. No. Wait, no. No, I don't like that at all. My apologies. It's not going to make that one any bigger. Oh, that was my first gut reaction. But looking at the math, no, it's going to make that term bigger, which is going to go in the denominator, and that one bigger by the same amount. Oh, wow. Okay, that surprised me. Okay, so it doesn't change it. I guess that makes sense now that I think about that. Oh, I'm glad I did this one. Okay, good. Yeah, I didn't see that coming. All right, so I bend this down. I'm going to get more torque here, but I'm also going to get more counter torque by the same factor. Ah, nice. Okay. All right. I think that was the whole point of the problem. I learned something too. How do these forces depend upon theta? Doesn't. Nice. Okay. Hope that was helpful. It was to me. Take care.